Now we are going to look at the next operation, which is the difference operation. Okay, the difference operation is represented like this. I say the difference of A and B, or the difference of A with respect to B, is defined as follows, where X belongs to A. Okay, X is an element of A and X is not an element of B. So all such X's are part of difference of A and B. Just realize that A minus B over here is not equal to B minus A, because your B minus A is going to be what? Your B minus A is this. X belongs to B and X does not belong to A. Okay, so let us take an example. We are going to take the same example as previous one. Let us take this. Okay, I'm going to paste it down here. Over here, this is my A and this is my B. I want to find out what is A minus B. Okay, so my A minus B is all elements which are in A but not in B. Let me just also write it in words. The difference is all elements present in A but not in B. Okay, so let us see what is A minus B over here. A minus B is equal to all elements in A. So we are going to see 1. 1 should be in A, but it should not be in B. Actually, 1 is not in B, therefore 1 is an element of A minus B. Now let's talk about 2. As you can see, 2 is present in A, but it is also present in B. Therefore, 2 is not an element of A minus B. The same is the case with 3, but 4 is present in A and is absent in B. Therefore, 4 is going to be part of A minus B, and 7 again is not going to be part of A minus B. Therefore, A minus B is this. Okay, now let's see what is B minus A. B minus A is going to be all elements which are present in A but not present in, it is going to be all elements which are present in B but not present in A. So let us see, 2 is present in both B and A, therefore 2 is not a part of B minus A. 3 is also not part of B minus A. 7 is also not part of B minus A. 9 is only present in B, okay, and is absent in A. Therefore, I have 9 over here. And 11 is also only present in B and absent in A. Therefore, I am going to have 11 over here. Okay, so this is my set difference of A and B and B minus A. If I have to represent it using Venn diagram, I can do it like this. Let us suppose this is my universal set. Over here I have my A, over here I have my B, okay. Then the then the difference A minus B is represented as elements present in A but not in B. So we are looking at this region. Okay, this is the region which is inside of A but outside of B. Okay, so this is my A minus B set difference. Okay, and what would be B minus A? B minus A is going to be this. I have my universal set. Let us suppose I have A over here, I have B over here. Then my B minus A is all the elements or the region present in B but outside of A. So it is going to be this region. Okay. This is my B, this is my A, and this entire rectangle is the universal set. Right? And this is B minus A. So you can pretty well see that A minus B is not equal to B minus A. Right? Now let's look at some properties of set difference operator. Okay. Properties of difference. The properties are complement of A is equal to universal set minus A, or the difference of universal set and A. Okay. Next property is the difference of A and A is equal to the null set. Okay. Then difference of A and complement of A is equal to A. Okay. And this is also same. Right. Next property, we are going to see the difference of A and the null set is equal to A. Right. Then we have difference of A and B is equal to intersection of A and complement of B. Another property that we have is A minus B is equal to B minus A if and only if A is equal to B. Okay. One more property that we have is A minus B is equal to A if and only if A intersection B is a null set or A and B are disjoint. Okay, and the final property that we have is A minus B is equal to a null set if and only if A is a subset of B. Okay, so these are the properties that might be useful in solving some specific type of problems that we are going to see later. Now let's look at another operation, the last set operation. It is the symmetric difference. Okay, symmetric difference. So the symmetric difference of two sets is represented as this. Okay, this is known as the symmetric difference symbol. Okay, I define it as the symmetric difference of A and B is X, where X is an element of A minus B or X is an element of B minus A. Okay. So what this basically means is it contains all elements which are in A but not in B, okay, or in B but not in A. Okay, if you do the literal translation of this thing, you are going to get this. But in simpler words, what we are saying is it basically contains all elements in A or B but not in both. Okay, so we are going to see what this means using an example. So from this definition only, one thing is very clear, and that is symmetric difference of A and B is basically equal to, just look at this, your OR is union. Okay, it is equivalent to the union operator. Therefore I can say the symmetric difference of A and B is equal to A minus B union B minus A. Okay, let us take example. We are going to have the same example and we are going to find out the symmetric difference of A and B using this. So I have this example over here, right? And I want to find out symmetric difference of A and B. Okay, so as per this definition, we already have calculated A minus B. Where is it? Let us copy this. I'm going to paste it over here. Okay, now using this I can say that the symmetric difference of A and B is basically what? It is the union of these two. Okay, so it has 1, it has 4, it has 9, it has 11. Now as per my another definition which says it contains all elements in A or B but not in both. Okay, so we are going to just verify if it is true. As you can see, 1, it is present in only A but not in both, right? Similarly 4 is present in A but not in B. Okay, so it is not present in both. Similarly 9 is present in B but it is absent in A, right? So it is also not in both. And 11 is present in B but is absent in A, hence even 11 is not present in both. Therefore even this definition is correct, which says it contains elements present in A or B but not in both. Look, it does not contain 3 because 3 is present in both, right? And hence my definition of symmetric difference. How would you represent it in a Venn diagram? You are going to do something like this. Okay, let us suppose this is my universal set and I have my A over here, I have my B over here. Okay, let us just give the names A and B. Then symmetric difference is the elements present in either A or B but not in both. Okay, I know that this is the region which represents elements in both. Okay, so basically I am looking at this region and I am looking at this region. Okay, I just have to eliminate this region from my answer and I'm going to get the symmetric difference. Okay, so this is your Venn diagram for symmetric difference. Okay, let's look at some properties of symmetric difference. I'm going to write down over here properties of symmetric difference. And these properties are symmetric difference of A with itself is equal to null set. Symmetric difference of A with a null set is equal to A. Symmetric difference of A with a universal set is equal to the complement of A. Okay. Symmetric difference of A with the complement of A is equal to universal set. And finally, symmetric difference of A and B is equal to A union B minus A intersection B. Okay, you can take a look at this with the help of a Venn diagram. Okay, let us see how. This is my Venn diagram. Okay, and also others, you can either prove it in a very trivial fashion by the definition of symmetric difference, or you can use a Venn diagram to prove these properties. So we are trying to prove this right now. So let us see what is A union B. Okay, so if this is A and B, then A union B is going to be the entire thing. Okay. Now what is A intersection B? A intersection B is going to be something like this, right? This is my A intersection B. Now I am looking at A union B minus A intersection B. So from this whole region, I am subtracting this. Okay. So obviously, what am I going to get from this? If I do minus, then I am going to get this. This is my A, this is my B. Okay, so I'm going to be left with the following region, which is nothing but my symmetric difference of A and B. Okay, so this is A union B, this is A intersection B, and if you do a difference of these two sets, what you get is symmetric difference of A and B. Okay, same way you can prove the other properties as well. Now let's look at some other terminologies that are required in the study of sets. Okay, the first one that we are going to see is cardinality of a set. Cardinality of set is simply the number of elements in the set. Okay. So let us suppose that A is equal to 2, 4, 6, 8 and 10. Then cardinality of A is represented like this, and it is equal to number of elements, which is 1, 2, 3, 4 and 5. So I'm going to write cardinality of A is equal to 5. Okay, the symbol is this for you to remember. Okay, so that was about cardinality of set. Obviously it is only applicable to a finite set. Okay, so if it is an infinite set, the cardinality has no meaning. Now let's look at the concept of a power set. Okay, now I define a power set as like this. We say power set of A is the set of all subsets of A. Okay, set of all subsets of A. So let us see what do we mean by this. Let us suppose that my A is equal to 1, 2 and 3. Okay. So what are the subsets of A? Let us say A1. This is a subset of A, right? This is also a subset of A. This is also a subset of A. Similarly, even this is a subset. Even this is a subset. Okay. Right? And even this guy is a subset of A. We also know A itself is a subset of A. Therefore, I can say that this guy is also a subset of A. A7 is a subset of A because that is A itself. And when we talked about null set, we said that null set is a subset of every set. Okay, therefore A8, which is equal to a null set, okay, which is equal to 5, is also subset of A. Therefore, the power set of A, okay, represented like this, P of A, is equal to what? It is equal to A1, A2, A3, A4, A5, A6, A7 and A8. Okay, you can write it also like this: 1, 2, 3, 1, 2, 2, 3, 1, 3, 1, 2, 3, okay, and a null set. Okay, this is the power set of A. Now, one thing that I want to tell you over here is cardinality of power set of A is equal to 2 raised to n, where n is your cardinality of A. Okay, where cardinality of A is equal to n. Okay, so as you can see here, my A was having 3 elements, so the power set of A is having 2 raised to 3, which is 8 elements from A1 to A8. Okay, so this is one result that you should keep in mind. Okay, now let us take an example to better understand the concept of power sets. Okay, so I'm going to write an example over here. Let us suppose I have a set which is defined like this. Okay, A is this. Okay, and what I need to find out is the following sets. Okay, I have to find A minus 5. Okay, I have to find minus A. I have to find A union power set of A, and I have to find A intersection power set of A. Okay, so let us see how we are going to do this. For the first set, which is A minus 5, we already know the identity. when we did the identities on difference, okay, a minus phi is always going to be a. Okay, so you do not have to do anything about this. You're simply going to say that a minus phi is equal to a because we have the property, okay, due to property of set difference. Okay. Now what do we have? We have a set of an empty set minus a. Okay, so let's take a look at that as well. Set of an empty set minus a. So just understand one thing. We are looking at those elements which are present in this but are absent in a. Okay, so you cannot have phi itself, okay, because phi is present in both a and it is also present in this particular set. Okay, so the answer is going to be a null set. Okay, so the solution for this is, the answer is, it is a set containing nothing. It is this. Okay, just realize one thing, it is not this. There is a difference between this and this. This is not there because phi already is contained in a and it is also contained in this particular set. We are looking at a null set, right? Therefore we have this as the answer. This is a very important thing to keep in mind so that you understand the difference between a null set and a set containing a null set. Okay, so do not get confused between these two. Now next what we are going to try to find out is a union power set of a. Okay, so a union power set of a. For that, let us first find out what is the power set of a. So power set of a is equal to, let us also write what is a. A is given as to be equal to this and this. So I'm going to create a power set of a. It is going to have how many elements? It is going to have 2 raised to 2 elements. Therefore it is going to have 4 elements. The power set of a is going to be having a null element. Okay, then it is going to have a set of a empty set. Okay, then it is going to have a set containing b, and finally it is going to have a set containing a itself. Okay, so it is going to have a. So this is my power set of a. Now what do I want? I want union of a and the power set of a. So now I can easily tell that the answer over here is a union power set of a. Okay, we are talking about all the elements present either in this or in this. Okay, so phi is there. Okay, right, then this is there, set containing an empty set. This is also there. A itself is also there. Do we have any more elements? Yes, we have B also present. Okay, so this is the union of A and power set of A. It contains all the elements which are present in A or which are present in power set of A. Okay, in the same manner I can also find out what is the intersection of A and power set of A. I am looking at those elements which are present in both A and power set of A. So what is that element? B is not present in power set of B, okay? Because there is a difference between B and a set containing B, okay? You cannot treat them as same. So this B is different from a set containing B, right? So what we see over here is the only element that is present in both A and power set of A is the null element, okay? Hence, my intersection of A and power set of A is equal to null element. So I'm going to write this. Oops. Let us use the different color. So this is my intersection of A and power set of A. So let us understand another concept from the same example. As I told you, these two are different, okay? So how you are going to understand the difference? Just understand this. The cardinality of this set operation is 0, okay? Because it is having no elements in it, okay? So I'm just going to write over here this minus A is equal to 0 because it contains no elements, okay? While the cardinality over here, A intersection P of A, is not going to be 0 because it contains one element. The answer is a set containing a null element. As we had seen, the null element is common in both of them, okay? Therefore, the cardinality over here is 1, okay? So this is something that you should understand and keep in mind. The cardinality of null element is 0, while the cardinality of a set containing null element is 1, okay? Now let's talk about some laws that govern the set operations, okay? These are the same laws that we studied in proposition logic, okay? The only thing that changes over here is if you replace your AND with intersection and you replace your OR with union, you replace true value with a universal set, okay, and you replace a false value with a null element, then you're going to be able to get all the laws from the laws of propositional logic, okay? So just like we had the commutative property in propositional logic, we have the commutative property in sets as well, which says that A union B is equal to B union A, and the same is the case with intersection. The associative property also is similar. A union B union C is equal to union of A and B union C. As a matter of fact, the way in which you take the union or the order in which you take the union does not matter, okay? So that is your associative law. Then the distributive law is again same as the distributive law of propositional logic. A union B intersection C is equal to A union B intersection A union C, okay? And the other variant of this, obviously this is a dual of the above statement, as we already know from the concepts of propositional logic. Then we have the idempotent law, which says A union A is equal to A, and same is the case with intersection. The absorption law, which says A union A intersection B is equal to A, okay? And a dual of that, which says A intersection A union B is also equal to A. And finally the deMorgans law, which says complement of A union B is equal to complement of A intersection complement of B, and the dual of that is going to be complement of A intersection B is equal to complement of A union complement of B. Now we are going to see how we prove these theorems. Okay, so I'm going to show you how to prove the distributive property. Okay, let's look at how we do it. Proof for distributive property. I'm going to prove that A intersection B union C is equal to A intersection B union A intersection C. Let's see how we actually do that. Let us suppose that we have an element of this particular set. Okay, let us suppose X is an element of this particular set. Okay, so I'm going to write it as X is an element of A intersection B union C. Okay, so for all X, I can write for all X, what I have over here is, I can say that X is an element of A, right? And X is an element of B union C. What I have done is I have basically represented the union, okay, by the they represented the intersection. By the definition of intersection operation, I can say that the element X belongs to the set A and it also belongs to the set B union C, right? There is no problem in this. So in the same manner, I can say that for all X, X belongs to A and X belongs to B, or X belongs to C. Now what I have done is I have simply expanded the definition of union. Union says X would be either present in B or present in C. So I have written it in words. I am saying X is present in B or X is present in C. Okay, so even this is true. There is no problem in this. Now what I can do is I can rewrite it like this. For all X, okay, I can say that X is present in A, okay, and X is present in B, or X is present in A and X is present in C. Okay, I have just rewritten this statement in this form. Okay, both these statements are equivalent. Okay, so now what I can do over here next is I can say for all X, just concentrate on this. I can write this as X is an element of A. What is AND? AND is intersection. Okay, X is an element of A intersection B, or X is an element of, how I can write this? I can write it like this. X is an element of A intersection C. Okay, now what I'll do is I'm going to take off this OR. Okay, what I'm going to do is I'm simply going to say this is equivalent to for all X, X is an element of A intersection B. What is OR? OR is union. So A intersection C. Okay, so now what we have right here is we have proved that for all x which is a element of this set, okay, it is also a element of this set. Okay, hence I can say that A intersection B union C is equal to A intersection B union A intersection C. In a similar manner, you can prove other theorems as well, okay, by taking an element which is belonging to a particular set and proving that it also belongs to this set. If you do that, you actually effectively prove that both these sets are equal. Okay. Now let's use the same concept to also prove the deMorgans law. Okay, so let's see how we do it. Proof for deMorgans law. We are going to prove that A, let's use a different color over here. We are going to prove that A union B complement is equal to complement of A intersection complement of B. Okay, so how we are going to prove it? We are going to take an element of this set. Okay, so I'm going to say let X be an element of A union B the whole complement. Okay, then I can say that for all X, okay, what is the meaning of X is an element of this? It basically means that X is not contained in A union B. Okay, so it basically means, or I'm going to write like this, X is not an element of A union B. Okay, so this basically means it is equivalent to, for all X is not an element of A, right, and X is not an element of B. Okay, I can say like this. Okay, there is no problem in this. So this is equivalent to saying that for all X is an element of complement of A, right? Because this is the definition of complement of A, right? And X is an element of complement of B, right? Even there is no problem in saying this. So even the statement is equivalent. Now this is equivalent to saying that for all X, what I'm going to do is I'm going to replace and with an intersection. Now I'm going to say for all X belongs to A complement and or intersection B complement. Okay, so now I have just proven that for all X which are part of A union B the whole complement, they are also the part of complement of A intersection complement of B. Therefore I can say that, therefore what I have is A union B the whole complement is equal to complement of A and intersection of B. Okay, in a similar way you can also prove other theorems over here, all the other theorems. Also you can even take the help of Venn diagram to prove these theorems. So let us try to prove absorption using Venn diagrams. Okay, so I'm going to write down over here proof of absorption using Venn diagram. Okay, you just have to show that both the regions are same in the two given concepts. Okay, in the two given sets we are going to prove, let's suppose this. Okay, so let us first draw the Venn diagram for this set. Okay, so let us suppose I have a universal set over here. Okay, now how I can represent A intersection B? My A intersection B is going to be like this, right? And this represents A intersection B. Okay, so let's write this as A, write this as B, and this is U. Then what I have over here is, this is A intersection B. Now we also want a A over here. So what I'm going to do is, I'm going to keep an A. Let us suppose this is A. Okay, this is A, right? Just I'm going to say this is A and this is the universal set. Now our set is saying we have to take the union of these two things. Okay, so the union of this particular region and the union of this particular region, what is that? It is obviously equal to this. It is equal to A itself. Okay, so the answer, or we have just proved that A union A intersection B is equal to A, because this is the same region. Okay, so over here we have A, over here we have the universal set, and this is A. What you can do is, you can take a union of these two over here and you are going to get this same image. You are going to get A itself. Okay, therefore you can say, or you can write over here, hence A intersection B, or let's write it like this, A union A intersection B is equal to A. Okay, so this is how you prove using a Venn diagram. Let's take another example so that the Venn diagram method is clear to you. Okay, what we are going to take is, let us have the deMorgans law itself in the Venn diagram. Okay, let us have this. So proof of deMorgans using Venn diagram. Let's see how it looks. We are going to prove that A union B, the whole complement, is complement of A intersection complement of B. Okay, so let us draw the Venn diagram for this. So for this I have my universal set like this. I'm going to have A, I'm going to have B. Okay, now A union B is what? A union B is this whole region. Okay, so this is my A union B. Now I want to take the complement of this. So the complement of this is going to be something like this. I have my A, I have my B, right? And the complement is all the region which is outside this shaded region. So the complement is this region, right? So this is what? This is your A union B, the whole complement. Okay? Now what I want to do is I am going to find out what is this. Okay? So let us draw A complement. Okay? So my A complement looks like this. Okay, this is A, let us suppose. I'm going to put it as A. A complement is going to be this. It is the region outside of A, right? And I'm just going to copy this and I'm going to paste it over here, and I'm going to say that. Let us suppose this is B. So your B complement is also going to be the same Venn diagram where this set represents B. So this is A complement, this is B complement. Okay, you're looking at the intersection of A complement and B complement. Okay, so obviously what we have over here is the intersection of A complement and the B complement is all the region or the entire region which is outside of A and B. Okay, the intersection of this is going to be this. Let's suppose this is your A, this is your B. Okay, so I have a A over here, I have a B over here, and this is the universal set. So the intersection of complement of A and complement of B is the region which is outside A and outside B as well. So we are looking at this region. Okay. Now if you look at the two figures, if you look at this particular figure and if you look at this particular figure, you are going to see that both the figures are same, both are depicting the same region. Okay, therefore let us call this figure as figure A. Okay, and let us call this figure as figure B. What is figure B? Figure B is complement of A intersection complement of B. Now what we have over here is from figure A and figure B, what we realize is A union B, the whole complement, is equal to A complement intersection B complement, because since, or rather, they depict the same region. Okay, since they depict the same region or same set of elements. Okay, so this is your proof with the help of Venn diagrams. If you can prove that the Venn diagrams of two sets are same, they are showing the same region, then you can safely say that those two sets are equal.